Yeah, folks, welcome back to Advanced Data Mining and Machine Learning Methods. Yeah, this week it's a kind of lazy week because we have this public holiday on Thursday, meaning that, of course, this week also we keep it a little less busy. So we are going to talk about this supervised feature selection topic or chapter in this week and stop after this one here. Yeah, and maybe to get the bigger context where we are moving around, so to say, or fooling around, so to say, is, yeah, we're talking about high dimensional data. We talked last week about the challenges of high dimensional data, the curse of dimensionality, that brings a lot of quite unintuitive things with high dimensional data actually. And the most important problems come actually from redundant features and especially irrelevant features. Yeah, that was the big problem of the curse. Yeah, we talked about the curse or the blessing of dimensionality, because there is also a blessing if we have a lot of relevant attributes, of course. But if we have just irrelevant attributes, that was the basic assumption around most of the things that we observed that are really bad in high dimensional cases. So if we have irrelevant features, then we have the curse, and we want to get rid of them. Yeah, and we also want to get rid of redundant ones, of course. Yeah, because of scalability, efficiency, and stuff like that. So that's the bigger picture. And the first part here on supervised feature selection is about getting rid of irrelevant and redundant features. Of course, we will do that also here in the feature reduction metric learning chapter. And a special case of these kind of things here will be then in the bigger part on clustering high dimensional data. Yeah? So we'll start with supervised feature selection. And before we go into the details here of these methods mentioned in these sub chapters here, we have first of all, again, a kind of global view. What are we actually doing? What are we bound for in this chapter? So feature selection is in general the task of removing irrelevant or redundant features, as we just said. Yeah. Why? Well, because irrelevant features are not useful for a given task and probably decrease the accuracy and increase the risk of having a curse in the dimensionality and not a blessing. And why also redundant features? Well, redundant features meaning that there are two features which have more or less the same impact on our patterns. So why should we keep both, or why should we remove one of those? Well, typically redundant features are first of all strongly correlated features. Yeah. And they do not drop the accuracy by say, but they may drop efficiency, they may drop explainability, and they may also introduce a bias. In that case, it will also again drop efficiency. Yeah, so strongly correlated features can be good, but very often introduce a bias or whatever, and especially drop efficiency and explainability. So we want to get rid of those two kind of features. Because deleting irrelevant and redundant features can improve the quality and the efficiency of the methods, and of course also the quality and the interpretability of the patterns that we find. Yeah? And that means we try to come up with a new feature space where we try to delete all useless features, useless in the sense of above, irrelevant or redundant, from the original feature space. So that means we do not come up with new features, but we work with the original features, but simply try to see or evaluate for each original feature that we have whether or not it's useful or not. It's redundant, then get rid of it. Is it irrelevant? Then get rid of it. Yeah, but we don't change actually the feature space, so the feature space remains the same, or at least the features. Yeah, the features remain the same. So we just reduce the features. Yeah, so that is feature selection. That is also called sometimes dimensionality reduction. Yeah, so we just get rid of some of the features. Yeah, the terminology is a little bit different because people, if they talk in the community, if they talk about dimensionality reduction, they do not mean feature selection, because typically feature selection, dimensionality reduction, is also coupled with coming up with new features. So that is the difference actually. And we will see later on next week some methods about dimensionality reduction actually. And feature selection is also not feature extraction, where we typically extract again new features. So dimensionality reduction is about deriving new features from the original original ones, and feature extraction is more or less the same, but also again not dimensional reduction. So there is a kind of unintuitive terminology used in the community and used by people. So just that you know. Okay. So once again, why should we get rid of irrelevant and redundant features in our data set? Here is the motivation for an unsupervised case, where we have, in the two-dimensional case, there are two clusters, obviously. But if we just have a look at this feature here, we see that this feature is completely irrelevant in order to actually discriminate between these two clusters. It's even worse because we don't see any of these two clusters here in this feature. So this feature is completely irrelevant. This feature here is relevant, obviously, because in order to discriminate between those two clusters, we need this feature actually, this x-axis here. So feature y is irrelevant because if we omit x, if we only look at y, we have only one big cluster and no pattern anymore that we probably could have found. And here is an example on the right hand side for redundancy. So you see that we again have a clear pattern with two clusters. And actually both of these features here, x and y, would do a good job in discriminating between those two things. X may be a little bit better because the difference between those patterns is a little bit higher here than here, but both features would actually do the job quite good. So in that case, it means that those two are probably, or not probably, they are redundant, because they have more or less the same information with respect to the pattern that we look for. So in that case, we could omit one of those two also. Here in that case, we would omit y, of course. Here in that case, we could choose between y and x and just keep one of those two. So that is the example for an unsupervised case, and we also have an example for the supervised case. So in that case, you see here that kind of irrelevant feature would be this feature here. So this is a good feature actually. In that case, on the y-axis, the x-axis would be completely irrelevant, because if we just project all the points on this line here, on this feature here, on this axis here, we could not actually separate the two classes very well. But we can do that if we project them on this feature here. So in that case, x would be irrelevant and y would be absolutely irrelevant in that case. And redundancy could be somewhere here. So both features are actually redundant. They more or less have the same information. So combining them does not yield actually a better or easier problem. So in classification, in the supervised task, we want to discriminate between, in that case, two classes, obviously green and red. The same here, of course, green and red. That's hard in any of those projections here. That's hard also in the two-dimensional case. It's also hard in each of the one-dimensional projections. But it's more or less the same. So the hardness, the challenge of the problem is more or less the same. So in that case, both features are redundant. So meaning we could just drop one again. So I just want to stress that relevancy or irrelevancy shouldn't be judged on a pairwise basis, or individually, because in high-dimensional cases, many different things can happen. And this is a good example where things happen which are on the first glance quite unintuitive, but if you think about it, it makes absolutely sense. So we have two highly irrelevant features in that case, x1 and x2 are extremely irrelevant in order to discern or discriminate between green and red. But if we take the combination of both, you see that the task, or the classification task, gets a little bit more clear. It's still hard because it's not a linear problem, and we have to apply different or a more complex model on that. But at least it is doable, as you see here. Yeah, we just have to see or find those separating hyperplanes here in that case. Yeah, and we couldn't do that by just looking at x1 or x2. If we just look at x1 individually or x2 individually, that's absolutely a nightmare. Yeah, so just that you see that the combination of two irrelevant features might be or might produce a relevant attribute, or a relevant space, so to say. Yeah, and in that case, if we add a lot of those things that are individually irrelevant but together are absolutely relevant for our task, then again it's a blessing of dimensionality. Yeah? So just keep that in mind, that irrelevant features, or features that look irrelevant by themselves, may be in combination with other features very, very relevant, and that makes the whole problem, or the whole task of finding relevant and irrelevant features, of course, very, very hard. Yeah? Makes sense, hopefully.